Well, good afternoon. Can everyone hear me well? All right. Um, we're talking about two very important things. We're talking about what's called K-theory, and the story that Professor Caddison told that I read out last time shows that this it explains how K-theory arose in the early 1930s in discussions between von Neumann and other people, students and postdocs, a student and a postdoc, and they were talking about idempotent elements of a ring, unital ring. Or if it's a star ring, if it has adjoint, if it has a star operation, then they're called projections. If they're self-adjoint, they're called projections. But what Grothendieck noticed, who wasn't around then, but he was around soon later, and he worked on operator algebras and other aspects of functional analysis before he went into algebraic geometry. And and one of the things that he did, one of the very notable things that he did, he was considered to have revolutionized the field of algebraic geometry and also introduced important ideas earlier into functional analysis. But the idea that he put to work in algebraic geometry is basically to look at idempotence in a ring and look at the Murray von Neumann equivalence relation between them and the addition relation, and then the fact that these are equivalent. Murray von Neumann equivalence of idempotence is compatible with addition when two idempotents are orthogonal. So the sum is an idempotent. So you get a semigroup that way, and abelian semigroup, or monoid because there's a zero element. And then if you turn that into a group, if you embed that in a group, the way the natural numbers get, counting numbers get embedded in integers, and that's a special case. The case of a field is exactly that case. The projections in the idempotents in matrix algebras over a fixed field, they're determined up to similarity by a natural number, the dimension of the subspace they define acting on multiplication on the algebra. They talk about matrices acting on the finite dimensional vector space. Then the equivalence classes of idempotents with addition when the sum is a projection, the sum is an idempotent. That forms a abelian semigroup, and you from that, which is just it's the natural numbers, right? Because two finite dimensional vector spaces are isomorphic if they only have to have the same dimension. And isomorphism of the you have these projections, these idempotent operators on the finite dimensional vector space, and if you look at the range, then two of them are going to be, in fact, they're going to be similar, not just Murray von Neumann equivalent, but similar if and only if their images or ranges have the same dimension. So and if you take the sum of two orthogonal, sufficiently orthogonal idempotents, if the range projection, if the range subspaces are independent, then the range of the sum is this direct sum it's the sum of the ranges, and the sum of two independent subspaces. The dimension is the sum of the dimensions. So your natural number is you have a semigroup which is in one-to-one correspondence with these Murray-Phenomenon equivalence process. Now, this reason I'm not going through it in detail right now is that it's in the book for one thing, but I don't want to emphasize it right away because it's quite computational. It's quite the fact that if you have the fact that the addition of orthogonal idempotents and equivalence is that these are compatible, you have to work, right? Whereas for the definition for modules, which is equivalent, is very simple. In fact, it goes far beyond. Not only does it go beyond the modules which are pertinent for K theory of K0, defining K0, but you can consider an arbitrary class of objects. Suppose you have so this is recapping in a slightly more streamlined way, something I was doing earlier. So if you have, suppose you have a class of objects and the notion of isomorphism, okay? So they might be groups, they might be modules, might be just about anything where you can take the sum. So x plus y makes sense, okay? So x plus y makes sense. So it's and in the case of subspace, in the case of finitely generated vector spaces over a field, which is what you do for computing K0 of a field. When you compute K0 of a field, and you look at finitely generated vector spaces, and you look at direct sum and isomorphism, and you show that the direct sum is compatible with isomorphism, but that's very easy, okay? And so first of all, so we want addition to be compatible with isomorphism. So we have an addition of direct sum for vector spaces or modules, and this should be compatible with isomorphism. And well, so that means that the isomorphism classes, you can add the isomorphism classes, right? And it means that if you want to add isomorphism classes, you have two of them. You look at representatives and you add those, and it's going to be independent of the representative. Okay, and for in general, we're just assuming that, and if it's modules and taking direct sum, then it's a very easy exercise, right? Okay, and and also we want x plus. So that's one thing we want, and we want x plus y is isomorphic to y plus x. Okay, if you interchange the order of addition, then that you get isomorphic objects. And this is true for vector spaces, true for modules, right? Take the direct sum of two modules. Doesn't matter which order. The definition is ordered pairs. Ordered pairs, you can't just reverse the ordered pair and get the same thing, but you get something that is what's called isomorphism. An isomorphism between these modules if it's modular. So this is an axiom now. And also, you assume that, what this does is make the semigroup, well, it's not a semigroup yet, but it makes the addition abelian. So it makes sense to, so the plus sign was a good notation, okay? A priori, you don't know it's abelian, it's just an operation, a binary operation, and it's compatible with isomorphism. And then what you assume is that the isomorphism causes, when you add them this way, that's abelian. So operation on isomorphism causes is abelian. That's what this says. And then the third axiom is that we want the operation to be associative, right? We want to get a semigroup. A semigroup, you have an binary operation. Doesn't necessarily abelian in general, because you don't have that semigroup is not necessarily abelian, but this one is going to be. But it definitely should be associative, right? So we want to take x. Well, if you first add x and y, and then you add z, this should be isomorphic to what happens when you take x first, and then y plus z separately together, so separate from x, but together. Okay, so if this says the isomorphism classes are associative, right? Now, by the way, I'm doing this for a reason, okay? Because there's a very interesting example, which is not just modules. It's the case of what's called topological K-theory, it's a special case of C-star algebra K-theory, Urbanic algebra K-theory. It was introduced after Grothendieck by Mattia and Hertzebruch. So the history of K-theory, it started with Moraine von Neumann, was adapted by Grothendieck, applied algebraically, and then it was adapted to topology by Tia and Hertzebruch, which was already a special case of operator algebras, but they were studying C-star algebras, if you like, not von Neumann algebras. So they were looking at commutative C-star algebras. But then some people, after Tia and Hertzebruch, people noticed that it would work for arbitrary C-star algebras, which is sort of almost full circle, okay? But because the work of von Neumann and Murray was obvious that we work for arbitrary algebras of operators. Okay, so but the axiom 4 is there's a 0. Okay, so 0 plus x is isomorphic to x. That means the semigroup has a 0, what's called a monoid. A monoid has a neutral element. It's a semigroup with a neutral element. And by the way, anytime anyone has a question, just raise your hand. Is there someone? Rishi, where's Rishi? Okay. But so it'd be nice. Well, we don't have any. It seems we don't have anyone at the moment. No one recognizable on online. Okay. Well, this is just like the old days, where what you see is what you get. Okay. And yesterday there was an announcement for a seminar in the math department. Well, it was the annual, always held number theory seminar. And but one of the things mentioned in the announcement was we're not planning to have an online component. That we prefer to have just work with people that are present and in physical proximity. Okay, so this is So the first three properties say that we get a semigroup. Okay, and then if you throw in axiom 4, it's what's called a monoid, and that might be important because the zero element for a semigroup may have a zero element, but it's not necessarily unique, and so a homomorphism between two semigroups. Well, no, the neutral element will be unique if it exists, but still the homomorphism between two semigroups may not take the neutral element into a neutral element. It'll take it into an element which is neutral for the image, okay? But that's not the same thing if it's not surjective. So, where if it's a group, then it's an exercise in groups that the neutral element has to go into the neutral element, just if it preserves the group operation. Okay, so and we want to consider K0 as a functor. Well, this is much more general than K0, but this semigroup will be a functor, right? But we want the zero element. Well, we want the if we have a well, this is quite this we don't have we don't have the category. So here the field is a special case of a ring, and the modules are modules over a ring. So we don't quite have, and then the K0 would be a functor from rings to groups, okay, dealing groups, and the but if it's in the first instance, we don't have the groups, we have semigroups, and we'd like to know that that if you have a homomorphism between the rings, then the corresponding semigroups, the map between them, takes the zero element to the zero element. So you should think of it as a monoid where the zero element is actually emphasized. Okay. But so the special case of algebraic the algebraic setting that with rings that von Neumann and Grothendieck looked at, that's that's taken care of by this, where the and it's easiest to look at in terms of modules, okay? Because the idempotents are really quite technical point of view, and therefore even from a conceptual point of view, it's slightly intricate. It's a little could be even confusing. Okay, so but then it's an exercise. If we look at modules over rings, and the modules are the ones that one looks at in K-theory, finitely generated and projective, which means a direct sum of a free module being a direct sum of copies of the ring considered as a module, left module over itself. Okay, modules over rings. This is equivalent to looking at the group that you get, so and the associated semigroup and the group, associated semigroup and group. That's equivalent to looking at idempotents, okay? Not just in the ring, but idempotents in matrix algebra. But to turn these into a semigroup and therefore into a group, you have to work, okay? And that's the kind of thing I'm going to suggest we do it at home and look at the book, okay? And whereas the modules, if it's modules, then it's easy to see these axioms hold, right? And if the axioms hold for this class of objects, then you turn the isomorphism classes, so there's a notion of isomorphism. So there, then the isomorphism classes turn into a semigroup, right? With monoid, and in fact, you get a group. You take the enveloping group, every semigroup. So that's another exercise. What is the what's called the universal enveloping group of a semigroup? It's a good exercise. That's what the K0 group is. You construct for a particular class of objects, namely the easiest to say. You look at the finitely generated projective modules um, over the ring. And, okay, but now, so this is fun. I think it's always fun and enlightening, beneficial to pare down the situation so it's as abstract as possible. Okay, so some people complain about mathematics, saying it's too abstract, but in fact, abstraction, the power of abstraction, is what makes the world go around. Okay, and it's mainly exhibited in mathematics. You could say it the other way: if it's abstract, then it's mathematics. Don't quote me on that. I'm not quite. I'm still working on that. But is the microphone catching? If it's necessary, I don't know if it's necessary, but I hope everyone can hear me and it's not too soft or too loud. Okay. So one of the things I'm working up to is the Atiyah, as the work of Atiyah and Hertzberg, two well-known mathematicians of the 20th century. Atiyah, Atiyah definitely just passed away a few years ago. Hertzberg somewhat before that, but I guess into the 21st century. All right. Well, and they were looking at topological spaces, right? So say compact topological spaces, and make a Hausdorff if you want. And they were wanting to get a group, right? I mean, they were talking about topological K theory, and they wanted to take what Grothendieck did for algebraic varieties and do it for topological spaces. Now you could say they should have just taken the commutative Easter algebra of continuous functions on the compact space, continuous, say, complex valued functions, and then look at the modules and find look at isomorphic modules, adding modules, and noticing that isomorphism is compatible with addition, and getting a group that way. But what they did is something that doesn't fit into modules directly at all, okay? And in fact, it takes what's called the Serre-Swan theorem to turn it into modules. It's not quite trivial. But are some people familiar with the work of Atiyah and Hertzberg, what's called topological K theory? Well, you might have run across it, heard of it. But but I guess everyone has heard of a vector bundle. Right? Okay, vector bundle over topological space. If the topological space is a single point, then a vector bundle is a single vector space. And usually you take the fibers, what are called the fibers, the vector spaces associated to the individual points of the space. You take the fibers, you assume the fibers are finite dimensional. Okay, so there's a notion of vector bundle. I won't say exactly what all the axioms are at the moment, but it's a family of finite dimensional vector spaces parametrized, if you like, by a topological space, labeled by a point in the topological space. And so if you have two, just like vector spaces over, just like bundles over a point, you have two vector spaces, you can take the direct sum. Well, if you have two vector bundles, you can take the sum. And this is another bundle over the same base space, okay? So those are objects. They're not modules. They're not modules anymore. These vector bundles are not modules. They can be associated to modules. They even that's the Sarah-Swan theorem. The vector spaces are vector bundles and modules of that kind over the ring of continuous functions. They're the same. They behave in the same way. Okay, but that's not the route that T and Hertzberg took. They just said, look at vector bundles. And so, but they come under this class of objects, right? There you can take a direct sum of two vector bundles. You just add the vector spaces for each point. You have the vector. You have the fiber for one. What's called the fiber for one of the two bundles, and you have the fiber for the other of the two bundles. You just add them. Okay, just like for a single point, you take the direct sum, and that gives you a. if you're ingenious enough to put a so the this family of vector spaces is it's a you can take what's called the total space. You can just take the disjoint union of all these fibers. So like if you have r squared and you think of the y-axis as a fiber over 0 and then translating the y-axis giving you fibers over every point. This is an example of a trivial vector bundle over the real line, which is not compact. It doesn't matter, locally compact. And well, and if you look at the total space, then that's r squared, okay? And that has a topology. And the okay, so that's vector bundles. You can add them, and that's compatible with isomorphism. Of course, you have to say what the structure is. Well, it's pretty simple. It's just the combinatorial parametrization of the fibers by the base space, and then the fact that there's a topology, and you want some compatibility, but you want there to be enough. You want there to be lots of continuous functions from the base space to the whole to the total space. What's called the total space. Okay, this could be an exercise to work out, or even if you want to include the Sarah-Swan theorem, it could even be an essay topic. How is the Tia-Hertzberg theory in terms of vector bundles? How is their definition of K0 that way? How does it compare with the K0 over the C-star algebra of continuous functions on the space? But but anyway, that's this applies. These axioms hold for the vector bundles, and so you get a semigroup, abelian semigroup in the group, and they called it K0 of the topological space. it's a functor. It was because to go between the space and the algebra functions on it, the arrows go in the opposite direction. It's a contravariant functor. For rings, going from rings to groups, it's a covariant functor. Actually, the easiest way to see that is just to use the definition in terms of idempotence. So, in terms of idempotence, if R is a ring and S is a ring, and you look at maps, well, you don't even in this case have to look at maps going from to take the unit, taking the unit to the unit. But in the category of rings, you'd look at unital maps. But then if you have an idempotent, this is a homomorphism, it preserves addition and multiplication. Then if E squared, if E is an idempotent, so E is equal to E squared inside the first ring, then well, then if we look at phi of E, we're not even using addition, that the map is additive, just that it preserves products. So phi of E squared will be equal to phi of E phi of E quantity squared will be equal to phi of E squared, which is phi of E, okay? So idempotents go to idempotents. So it's the map between the rings gives you a map between the semigroups of idempotents. You have to check that it's compatible, okay? But that's the functorial nature. Now, in terms of modules, you can do it too. So that's an exercise, okay? So I think that's a good exercise to, and it works. One nice thing about the module approach is it doesn't have anything to do necessarily with projective modules. You could look at arbitrary modules. I did forget to say there's an axiom 5 that the isomorphism classes form a set. Okay, which is important if you want to get a group or a semigroup, because that semigroup is supposed to be a set, not just a class. You start off with a class. Almost anything is a class. It's not a set. Like vector spaces are for various reasons. Even vector spaces of dimension 1 are not a set, because just sets with one element don't form a set. There are all kinds of sets that have single element. It's I mean, there's no such thing as a set of all sets, right? The set of all things doesn't. It's just, there's a simple reason why there's no such thing as the set of all sets. Is everyone familiar with that? That would say there's a largest set, right? Well, yes, but he was just explaining an earlier theorem, okay? The theorem of Cantor. So the way you explain that there's no largest cardinal number, if there's a largest set, then there's a largest cardinal number. But the reason that can't be true is a theorem of Cantor. Now, what is anyone aware of this? How many people are aware of this theorem? Yes. What is it? Okay. Well, that's a very good first answer. Okay, because the final answer is a special case of what you need to say in the final answer. Yes. Another suggestion. Yeah. Okay. And that's what you said. What's your name? Larry. You're Lawrence. Okay. Well, this is the second time you've given me your name. Okay. Thank you. Maybe people should keep track of it and see how many times I have to ask. So, and what was your name? Abu? Okay, I'm sorry. Not very good with names at all. How do you spell it? S-A-D. Okay, so said that. Good. Thank you. If you don't mind, I'll just make a note of it then. Okay. All right. All right. And Larry. Okay. Okay. So and don't forget. So so Larry. The reason what you said is a special case is that if you look at real numbers, then that's to be thought of as if you think of them in terms of 0, 1 expansion, then it's like functions from the natural numbers into this 0, 1 set, right? So it's and that's how you define the cardinal number 2 to the L of 0, okay? To the power L of 0, and that, but then that the theorem you stated says that that's strictly a bit larger cardinal number than just um, than the cardinal number L of 0. Okay, the power gives you a larger if what you're taking the power of is not equal to 1, the power just gives you a strictly larger number than the exponent. But then if instead of putting L of 0, you put the what's supposed to be the largest cardinal, then you get 2 to the largest cardinal is strictly bigger than the largest cardinal, and that's the Russell paradox, if you like. That's what Russell translated into non-mathematical terms. Okay, and that's a good exercise. Actually, whenever I read his story, I get a bit mixed up. Okay, whereas the mathematical approach is as clear as a bell. Okay. All right, but so the isomorphism classes should form a set, and there's a good exercise that if we're looking at finitely generated projective modules, then if that's the class of objects, then the isomorphism classes form a set. Okay, that's a good exercise. Mark it on your calendar. Okay. All right. And I think that people should take seriously my suggestion to look at the Sayre-Swan theorem as a possible essay project or extended exercise, if you like. You might have other ideas for essays. Okay. So what does the Sayre-Swan theorem say? Well, on the one hand, you look at vector bundles. Now, if you say a vector bundle, you don't just mean an arbitrary, continuously parameterized family of finite dimensional vector spaces in some sense. You want it to be what's called locally trivial. So you have to look up the technical definition of vector bundle. It's quite simple. The vector bundles on the one hand, and on the other hand, you have well, modules. You have on the other hand, you have modules. Okay, modules over vector bundles over X. X is maybe a compact space. Okay. Maybe Hausdorff doesn't matter so much. The modules over X, and we want well, If it's arbitrary modules, no one says you get a vector bundle, okay? If it's a vector bundle, you get a special kind of module. A certain construction gives you a special kind of module. And it's a finitely generated projective module, lo and behold. Okay? Oh, I'm sorry, over Cx. X is not a ring. You can't have a module over X, really. You have a vector bundle over X, but in this algebraic setting, you look at the algebra of continuous functions on X, continuous, say, complex valued functions. That's what one usually does. Not necessarily complex. Okay, so and so these are so it's very easy to go from a vector bundle to a module. Okay. I'll, maybe I'll in a short, just a few moments, I'll give a I'll say something in that direction. Someone else might want to say something. Anyone have any suggestion? If you have a vector bundle, so if you have a space and you have a whole bunch of fibers, which are vector spaces, so how do you get the well? So you get continuous functions on the base space. Let's suppose it's just the interval 0, 1, and it's compact. And so how do you get a module over continuous functions on the space on the base space? Well, that's a conceptual exercise, right? Conceptual. But then the computational one, more getting into the nitty gritty, is to prove that that module you construct is it clear. Not everyone can see this. So well, sorry. Okay, so so the proving that it's finitely generated and projective. Well, that's half of the exercise, and then the other half of that's half of the Sarah-Swan theorem. There's a certain construction gives you. The construction is maybe ingenious, but the fact that it gives you the module is not. That's kind of obvious. That's what you want to get finitely generated and projective. Okay, and then conversely, if you have a module which is finitely generated and projective, which means the direct sum and projective means direct sum and of a direct sum and of a direct sum of copies of a free module. Of a free direct sum of a free, and free is equal to free over R. R is a ring. Is R plus R plus and so on. Sum of some copies. It's a direct sum of some number of copies of R. Okay. So that's that's Sarah-Swan, which is it's a good exercise in the construction of K0, I think, in terms of modules, because there's nothing technical in the construction. If you start with vector bundles, you get a group. But if you have to prove that they're finitely generated projective modules, then you have to work. So that's why in this so-called abstract approach, up to now, the previous Wednesday and Monday, Friday, last Friday, I was talking about modules, direct sums of modules. But in fact, anytime you have a direct sum type situation which is compatible with isomorphisms, then you get this nice semigroup, which now you might a priori you might say, what's the application of this? And if it hadn't been for Thea and Herzebruck, I wouldn't have dared to indulge in this axiomatic, okay? However enjoyable it was. Well, I might have said you can do something like that as an exercise if you want. Well, it's still an exercise, I guess, to check the details, to work through it. I would recommend it. I would recommend it. Okay, so I'm sorry, this last bracket should include 5. Well, they all should include 5. Both should include 5. I guess, well, this isomorphism classes form a set that should be number 4, and then 1 to 4 are give you a semigroup, and then you add the 0 element, distinguished 0 element. I mean, in fact, if you keep your finger on it. Now, it's true that if you have the 0 element of a semigroup, it's unique, but it's not necessarily preserved by homomorphism. So that's what a monoid is. A monoid homomorphism. So monoid is just the same as a semigroup, except it does have a 0, unique neutral element. But the semigroup homomorphism just preserves the operation, whereas monoid homomorphism, by definition, preserves the 0, which you may want. Maybe it's not important for us because when you pass to the enveloping group, even just a semigroup homomorphism, forget about zeros, it will give you a homomorphism between the groups, and that will automatically take 0 into 0 because they're groups. All right. Any questions? Yeah. Sorry? Oh, not being preserved by a homomorphism. Well, well, sure. If you take a simple semigroup, in fact, just take the semigroup with the start with the element, just a single element 0. Okay, and if you'd have a homomorphism from that into itself, then of course it has to take the 0 into the 0 because that's all there is. But suppose that you take this semigroup which consists of 0 and you add a new 0. Okay, well, then the previous 0, the earlier 0, the previous 0 is not a 0 for the whole thing anymore. Okay, and now here's a map from this 2-element semigroup into itself. You take everything into the original 0. Okay, then but this will be a semigroup homomorphism in a trivial way. But the actual 0 will not go into the actual 0. It will go into the old 0, which isn't a 0 anymore for the whole thing. So this is what happens when the map is not surjective, right? It's mapping the 2 elements into the one single element, which is different from the whole set. Okay, so maybe that's the simplest example. Any more questions? Of course, we may have a few minutes to talk afterwards too. I mean, and if other people are, doesn't look as if people are coming in very fast. But anyway, I'll be. If someone wants to ask to discuss some point in the hallway, that's fine too. Okay, so I bought some other books. The Garrett K. Peterson analysis now. Okay, that's my textbook for the first half of this course, if you like. Usually is given in the fall, and this half is given in the spring. So if you want to do a makeup term, then you can look at this book. Of course, I'm joking because we don't, the things in this book which are most pertinent to this course will be will be repeated to the extent they're needed. We'll be talking about if someone hasn't taken this course, 7436, 436. Okay, well, another book. Well, here's the book by Lordem. Maybe some people have it online, but it's good to have. I like to have a copy. This is a hard copy. When I ordered them 1 year, by mistake they sent hard copy. And why was that a mistake? Well, they didn't charge me for hard copy. I guess maybe they'd run out of the soft ones. Okay, well then there's the grandfather book on K-theory of operator algebras by Bruce Blackadar. K-theory for operator algebra. So I'm saying for this course, I'm saying K-theory and operator algebra because it's two emphasizing it's two independent things. The K-theory is based on the operator. Historically, it's based on the operator algebras. I think I would say, and the operator algebras are to a large extent based on K-theory. So I'm jumping up and down about K-theory as a functor, K0 as a functor, but that's what you need to classify operator algebra. It turns out that you can't just parameterize the isomorphism classes in general. In some very extremely upright cases, well-behaved cases, you can parameterize not just the algebras in your class, but the isomorphism classes by the well-behaved parameter. For instance, an interval in the line or a Cantor set. Okay, but usually you can't. But nevertheless, there's when you can't, there's always a functor, the K0 functor, and you can hope to prove, and in many cases you can that if the algebras, if you want the algebras to be isomorphic, then of course it's necessary for the K0 group to be isomorphic. Now, the equals doesn't make sense, but isomorphism for two K0 groups, yes. But then if you're lucky, then that implies the algebras are isomorphic. And that's how I got a job, okay? All right. So maybe that's, it looks like we will have people coming in. Please feel free to ask questions.